In this video I want to talk a little bit about the limit comparison test. So the hypothesis is if we have two series, one with the sequence a sub n, one with the sequence b sub n, and they have positive terms, then if we take the limit as n goes to infinity of the ratio of their sequences and it equals c, some finite non-zero constant, then they either both converge or they both diverge. And it doesn't matter which one you put on top. The reason it doesn't is because it can't be zero and it can't be infinity. It has to go to a constant. It doesn't matter which one you put on top, you're going to get a constant either way. So I want to talk a little bit about how this one plays out with a couple of examples I have that we're going to do here. So now, not that the limit comparison test is the only way to do these, but I just want to show you how this is set up. So if I look at the series 1 over n to the 2/3 plus 1, and I want to show it either converges or diverges, well, I'm going to compare it to a series that I know. So we pick a known series that looks similar to this series. The series I'm going to choose for mine is 1 over n to the 2/3, because I know that when they're in this form, if they have an exponent that is greater than 1, it converges. If it's less than or equal to 1, it diverges. So I know this is a divergent series. So if I'm using the limit comparison test and I get a constant, I know that they both diverge. So the way this is set up, we do the limit as n goes to infinity. Again, it doesn't matter which one I put on top. I'm going to put the given one on bottom. So n to the 2/3 plus 1. On bottom here, I'm going to put the one that I chose, the one that I knew was divergent. Calculate this limit. Alright, if it comes out to be a non-zero number, we're done. So let's see how this is going to play out. Now notice in the denominator, I'm dividing by a fraction. That means I can flip it and multiply. Now, the thing about the limit comparison test, we are no longer concerned about the series. We are just focused on this limit. All we have to do is calculate it. Any limit calculating methods we have. So I have n to the 2/3 over n to the 2/3 plus 1. Now some of you guys might already recognize what this limit is, because we can kind of treat it like finding a horizontal of a rational function, even though it's not rational. We can see the similar growth rates. But I want to remind you of another method used for calculating limits. If as n goes to infinity, top goes to infinity, bottom goes to infinity, I have an infinity over infinity case. So I'm going to apply L'Hopital's rule. L'Hopital's rule says take the derivative of the top and the bottom, recalculate your limit. So if the limit is n goes to infinity, on top I have 2/3 n to the negative 1/3. On bottom, 2/3 n to the negative 1/3. Derivative of 1 is 0. Now we recalculate. Well, the 2/3 cancel. I have n to the negative 1/3 over n to the negative 1/3, which equals 1. As n goes to infinity of 1 is just 1, which is clearly greater than 0. It is finite. So we could say since 1 over n to the 2/3 diverges, then 1 over n to the 2/3 plus 1 diverges by, and you'll notice I use a lot of abbreviations when I do these, limit comparison test. So that's how the limit comparison test is used. The trick is finding a good series, one that you know something about to compare it to. Anytime you have something of this form, if this had been, I'm going to look, because I know I'm taking a limit, I'm going to look for something similar to this that I know whether it converges or diverges, because when I take its limit, I know I need to be able to calculate that limit if I'm going to say anything. Now my other example here, I've got the summation of cosine of n over 2n squared plus 5. So if our goal is to apply the limit comparison test, just as a reminder, the series have to have positive terms. Cosine of n actually oscillates between positive and negative. Not every time, so it's not actually an alternating series. It would need a cosine of pi n to have that, but it does go have negative and positive terms, and it always will. So this one we cannot use the limit comparison test on. So I'm actually going to do another test here in a minute, in another video, excuse me, not in a minute, as far as you're concerned, called the absolute value test for convergence, and that's the exact series I'm going to start with. So if you want to see how that one's done, go ahead and take a look at that video.